So this part, I will introduce how the actual underlying network layer receives the request from the system layer that I just talked, and how actually it runs the simulation. So network layer models this design space, the network design space of distributed ML, where you have a bunch of factors to model in, such as which protocol you're using, how many number of physical links you have, which network topology you're using, and whether you're modeling the buffering, the flow control, arbitration. There's so many network behaviors you want to model. Those are all factored in underlying the network layer. So yeah, just to reiterate, the network layer simulates all the actual network behaviors, such as the communication protocols you're using, the actual network topology, the bandwidth and latency per each link, and whether you're running in-network collective communications or not, the offloading to the NIC, the compression of the network, the network packets, the buffering and the arbitrations, and so much more. So you can think of all the network behaviors are being modeled in the network side. And to model and to support these complex modeling of different network aspects, we decided to offer you a easy plug and play manner of any network simulators, rather than we just provide you one single network simulator and say, just go and use it. And this is enabled by via the network API. So again, using the network API, we were able to plug in different network simulators with different speed and fidelity to model the network of various fidelity and behaviors. So the network layer in the ASTRA-sim framework is sitting under the system layer. So you can think of the system layer will talk to the network layer via network API to request to send or actually send or receive some message. And the network layer will simulate that, call back to the system layer. And system layer, once done the collective communication, will pass the pointer back to the workload layer. So that's how the entire ASTRA-sim simulation is running. Workload, dispatching nodes, and whenever required, calling the system layer to break the collective into single send and receive operations. And the single send and receive operation will be actually being simulated in the underlying network layer with the full-fledged network simulators. And once done, pass the pointer back to the system and back to the workload until you parse and simulate the entire Chakra ET as an input. Yeah, we give it to the network simulator. So in terms of the system layer, the input from the system to the network, I will cover it later. But it's like, hey, please simulate sending a message from this GPU to that GPU. And once you're done, let me know so that I can proceed to the next level. So until the system, it doesn't know which physical topology you're using. It will just, based on the logical topology, dispatch the send and receive operation to the underlying network. The network simulator will actually receive the topology file, bandwidth, latency, all those configurations, simulate the actual network behaviors, and call the system callback once you're done. So all the actual network behaviors are being modeled under this underlying layer.
Is it also hierarchical in nature? Let's say, like I want to do a part of this in much more detail, whether it's a chip layer or inside the node, but the rest I would like to keep it. Is it possible to capture such a things to be really simple?
So currently, until now, the use case was we plug in one network simulator we can plug in different network simulators with different fidelity, but in terms of one single run of simulation, we were only using one network simulator. But like you mentioned, if we want to model some part of network with different fidelity, I can imagine we can extend the API, instantiate multiple different network simulators, and call the network simulator whenever required. Because ultimately in the system and the workload perspective, yeah, it's nothing but, hey, simulate this and let me know when you're done. So technically speaking, yes, we can do that. It's just not. Yes.
The way ASTRA-sim works is it's really the network simulator which is running, and ASTRA-sim is kind of a library in that. And now you have two simulators running, so you kind of have like two processes running. So it's a little bit of that engineering which has to be managed. But I mean, technically it should be possible.
Yeah, in terms of the way the
Yeah,
framework is built,
that's-
there should not
Yeah,
be.
they should not be, just the engineering piece, because right now the event queues all sitting in one simulator.
Yeah, but if you think about, I just following your point about zooming in, we have a scale out.
Yeah.
And then scale up,
Yes.
and then within that we
Yes.
have,
Yeah.
and so it is a cascading
Yes.
set of networks. So
Yes.
today we build that all under one network simulator?
Yes, today we are building that all under one network simulator. Yes, that's true. Yeah.
Yes. So actually just, fast forwarding to enable the compute API, which we will plug in new compute simulators. We try to pull out some engineering efforts which can synchronize different event queues, stuff like that. So once it lands, I can definitely think of plugging in more network simulators with different fidelity should be much easier. But yeah, just at least for now, we haven't done that engineering effort for now, as we are just modeling everything, scale up, scale out in just one network simulator. But yeah, we are not limited by that. We can put some more engineering efforts and support those kind of simulations as well. Any more questions for now, please?
For a given SoC, because if garnet and let's say if we have GPU, but then the details are not properly.
So
Today that would come on the compute side. I mean, that would fall in the compute side of ASTRA-sim. Okay, like from the perspective of that. And so now again, similar to the previous answer, like whether or not you're modeling it depends on the fidelity of the compute simulator.
as well as I can also think of, the connotation we are giving is that, okay, one chakra ET is representing one GPU, and we are capturing what the GPU should do in terms of compute communications and remote memory access. And what ASTRA-sim models is get the chakra ET, parse what the chakra ET says, and dispatch the sim send and receive operation whenever required. But that connotation that one chakra ET file is capturing what a GPU is doing, we may just think of it as now what one chakra ET file is representing is, instead of one GPU, one P is doing things like that. And by that granularity, we can also capture those on-chip network simulations as well. So that's what I'm thinking. So yeah, we are collecting chakra ET at the GPU granularity, but I'm thinking if we collect chakra ET in terms of other on-chip granularity, I think we can model these systems as well. Thanks. More questions for it now? Yeah, if not, let me just proceed. So yeah, just wanted to discuss how the network APIs are actually being declared and implemented. So the most common network API we're using is SimSend. And as you can see here, it's saying, can you please simulate to send a packet with this size to this destination and call this callback once you're done, so that the system layer acknowledges this is done and can proceed to the next finite state machine states. And the counterpart of SimSend is SimReceive, which is basically saying, hey, I expect to receive a message from this source with this message size. Once you receive this message, please call me this callback so that I can acknowledge that. And even we have this API called SimSchedule, which doesn't really simulate any of the network behavior. Just say, please call me this callback after this delta time, or even some helper APIs such as SimGetTime, which is used by the ASTRA-sim just to query which simulation time I'm just currently at. So this is how the system layer is actually implemented. In this ready function I mentioned, we are dispatching the send and receive operations to the network. Here we are just calling the SimSend, SimReceive, the APIs. So the underlying network, which underlying network backend you're using doesn't really matter, because the system layer's perspective, you're only calling this API. So it's our job to bring a new simulator and implement this API so that this entire simulation ecosystem is working. So that's why, as an example, I just come up with some example API implementation. So that's why I just put a caveat saying the implementation may vary by which network simulation backend you're using. But for example, the API implementation of getting the current time in this simple analytical backend, I just query the event queue to give me the current time and return that. And how about the SimSchedule? This API, again, just to visit in more detail, say, please call this function with this argument after the delta time. So in an example implementation, what I do is I query the current time, get the event time, and schedule the events. So that was pretty much it for this metric backend. And the SimSend. This is the detail of the SimSend API, where I skip minute details, but basically saying, can you please simulate to send a message with this message size to this destination and call this event handler once you're done. So the SimSend implementation in the analytical backend, which is the simplest backend, by the way, is here. As you can see, I basically calculate the route, make a chunk, and start sending the message. And once the message arrives to destination, I will that will automatically call this process chunk arrival function, where here I call the event handler so that the system layer can understand that the send operation is done and proceed to the next stage. So this is ultimately how the network backend and the network API has been implemented, and how you're integrating new simulators, new network simulators to the ASTRA-sim ecosystem. So with that, we currently have 4 variations of network backends, but I really view it as just a reference implementation because we can plug in any network simulator by just implementing the API. The simplest one is being the analytical one, where you analytically model everything, which has the lowest fidelity, but the upside is you get high speed. Where in the other corner we have the NS3 simulator, which is a full-fledged inter-network simulation with buffer control, congestion management, and so on. The upside is you get more fidelity, but of course the downside is that it takes time to simulate very large-scale clusters. But ultimately, all these 4 networks are being integrated into ASTRA-sim by just simply implementing the list of APIs I just showed. So I'll skip the details, but the analytical backend, like I said, doesn't really model the huge network behaviors. Whenever the send operation is being requested, it will just model the link latency and bandwidth vectors and schedule the event once it's done. So the simulation is really fast. And because we are using the alpha beta model for large messages, it's still quite faithful. And yeah, it's fast, but again, the fidelity, when we have network congestions and we need flow control, the analytical backend may not be the best fit. And on the other way, we have the NS3 network configurations where NS3 is a really full-fledged network simulator where you can model this internode switches, top of the rack, multiple GPUs, spine switches, etc. So here in this case, as an input to the NS3, you can designate things like congestion control, buffer size, the cache size, and switch bandwidth latency, so much more. So, but ultimately, this NS3, how it's being integrated to the ASTRA-sim is nothing different from integrating the analytical back into the ASTRA-sim. So with that, I just, as an example, I just showed how we define new topologies in the NS3. We just define how many total devices we have, which is the number of switches plus the number of GPU devices. And you basically just list out the link information line by line. For example, here in this case, you're connecting 8 GPUs, ID from 0 to 7 to the switch, which is ID 8. So this is a one switch system with 8 GPUs. Whereas it can be more complex, like here, you have 16 switches to model this top of the rack and the spine switches, and you connect GPUs to this local switch, the top of the rack switch going to the spine switch. So in NS3, you can model this kind of complex networks. And once we run ASTRA-sim, the NS3 will run and model all the network behaviors, which will take more time, but again, with a high fidelity. So this really concludes the section of the network backend. And now we are at the coffee break, and I'm happy to take any questions.